All right, welcome back to animation part two. We left off here looking at cloth animation, and this was from the animated short Jerry's Game. And if you saw the Toy Story movies, you saw this character again. They reused him. He was the fixer in Toy Story 2. I guess if you spend all that effort getting a character like that, it pays to use them twice. All right. This is something called functional animation, which I think is just a really interesting combination of multiple things. So here's an example. The example is these outer colored circles are targets, and these inner colored circles have been thrown in this randomly, and their job is to go to their target. Okay, it's not unlike a crowd of people who want to move around and get somewhere. But the trick is you also want them to not hit each other. You want them to deliberately avoid each other. So getting them to move to their target, yeah, you could write an equation for that or do some keyframing. But getting them to avoid each other, like that's got to be more difficult, right? Because how are you going to keyframe that and keep it not looking awful? So here's a trick. It's called functional animation. And in functional animation, well, I like to call it fake physics. Don't ever use that term. Someone will get mad about it. But I think of it as fake physics because we're going to set up some physics that's not really there to make the objects behave the way we want them to, make them want to behave the way we want them to. So here's the first part of it. Well, if I want this dot to go up here, I'm just going to put a spring between them, stretchy spring between them, so that if I turn on physics, F equals ma, acceleration equals spring force over mass, the particle wants to go towards the target. This is the mechanical symbol for a damper, shock absorber. That is, it takes some of the energy out of the system. Otherwise, when this dot gets up there, it's just going to overshoot, like and go off the screen and then come back and then bounce around. We don't want it to do that. So we throw a damper in there as well. And we can set the stiffness of the spring any way we want, and we can set the value of the damper any way we want also. Okay, so now we've got the dots moving towards where we want them to desire to be. How do we keep them from colliding with each other? Well, I'm just going to make up a physics equation to keep from wanting to hit other dots. And I'm just going to make up a repulsive force. And my repulsive force, again, I'm just making this up, is some repulsion coefficient. I can make it really repulsive or only a little bit repulsive, times the distance between the objects raised to some power. So the coefficient in the numerator is just sort of an overall, how repulsive do you want these things to want to be? And the thing at the bottom is they get closer and closer. D gets smaller, but the denominator gets bigger. As they get closer and closer, they more desperately try and push each other away. And the power also is a measure of how desperately do you want them to push each other away. And so if you assign all this to the particles and turn them on and turn on A equals F over M, well, you get stuff like this. And here it is with a low stiffness, medium stiffness, and high stiffness. Here you can see particles that are deliberately trying to step out of each other's way. And I didn't have to animate that. I didn't have to tell it to do anything. I just had to set up equations and turn it loose. And you can see that as you increase the stiffness, they more desperately try and get out of each other's way. You can see the little stuff going on here. I can just envision two particles coming together like you do when you meet someone in the hallway, then you both shift to the same side, then you both shift to the same side. That's probably what was going on there. So you have complete control over the nature of how the physics are being concocted, but you don't have to, other than setting up the equations, you don't have to do the animation yourself. Here is changing the repulsion coefficients. That's C. Here it's 10. Here it's 30. Um, it's only a little bit different, but you can see some differences in how desperately they're trying to step around each other. And there's a avoidance an avoidance video where you can watch all this in action. And I'll show some of it in the demo video too. All right, final thing to put here in the animation is motion capture. Like everything else, you flag yourself as a newbie if you actually use the correct words for it. Everybody calls it mocap. Don't ever call it motion capture. And it works like this. They have suits. There's companies that make these. They have suits that either have reflective ping pong balls glued to them or LED lights. And there's cameras in the corner of the room. So here's a guy wearing one of the suits doing some skateboarding. And you can't really tell very well, but there are lights and cameras in the corner of the room, and they focus in on the moving lights or reflective ping pong balls, and they triangulate them into XYZ coordinates. And so here the actor is moving, and there's the character that's coming off the coordinates that are on the suit. So this is called motion capture. So if you're playing a game and somebody seems to be doing an amazing job on the screen of kickboxing, that's probably motion capture. Something elaborate like kickboxing would be very tough to keyframe, impossible to do with physics. So yeah, so motion capture really is everywhere. You can motion capture faces too. There's a new TV show on, something that's derived from The Masked Singer, I think, where I think they have people put one of these on and sing, and some animated character. It looks like their voice is coming out of a computer graphics animated character. I really dislike shows like that, but I may just have to watch this one. But anyway, it's not only capturing mouth motions, it's capturing eyebrow lifts. Some of these even capture movement of the eye, like you roll your eyes, like your parents told you not to, but you did anyway. That could be captured here as well. And then here's the part I find truly amazing. Click. You can mocap animals. Now, I have a cat, and my cat would never put up having little white reflective balls glued to her. It's just out of the question. Don't even think about it. But apparently some cats will put up with this. And so they even mocap animals now. This is from the first movie Tron. These are some animation examples. This is from the first movie Tron. The motorcycle's going around this corner. They just keyframed the lean angle. It's all wrong. It just looks horrible. They really could have benefited from some physics. This is a movie called Card Trick. It was made by one of our guest speakers, a guy named Rob Russ. He did this as a student, as a college student, and won a Student Academy Award for doing it. We'll look at this. And Rob, like I said, is one of our guest speakers because he is now at Pixar and was the lead animator on Toy Story 4. And then we'll look at this too. This is a series of Pixar animated shorts that they made for ABC Saturday morning cartoons. So we'll look at some of that. But as we look at it, look at all the different things going on. Is a lot of these will have a lot of keyframing in them. Some things you can say were probably done with equations, like the breathing King of Diamonds. There's no point keyframing that. You can write a little script and put an equation in there. Um, I'm sure, some things you'll see in these were done with mocap. So yes, animation, big deal. But even though we're not doing serious, sophisticated animation here, Professor Zhang teaches a whole 1/4 course on animation in which you'll do a lot more, but it's worthwhile for all of us to know something about it.